Can you guys hear me? Can somebody reply in chat if they can hear me, please? Just got a little bit of echo, so I'm guessing yes. Cool. We'll give it a couple more minutes, and then we can begin. So I thought I saw a bunch of people were waiting, and now I see 4. So I'll give it to 5:35. Give me 1 second. I need to find a power cord. All right, we're gonna get started. I'm gonna do one last audio check. Can you guys all hear me? If you could reply in chat, that'd be great. Awesome. Okay, so I don't do a lot with YouTube, so I'm not really sure. I'm gonna try my best to check chat every once in a while to see if there's any questions. But please just try to queue them up. Know that I won't be kind of checking back here too often. I'll definitely check towards the end. But anyways, okay. So to frame this up a little bit, so I do this in a lot of semesters, and it usually is useful, especially for the teams that are working in data science or machine learning or quote unquote artificial intelligence. That we're being exposed to some of this stuff for potentially the first time, and so I found it useful to kind of bootstrap some of your knowledge in this area to help get you pointing in the right direction, thinking about the questions to ask, and so forth. So this is just supposed to be like an introduction to machine learning, kind of like a 101. I am more than happy to go into more detail in anything and everything. I have a lot of passion around this topic, and I'm happy to talk with you all individually. I'll probably be getting very involved as you start doing development and start doing analysis as to your methods and your methodology and analysis that you're going to be using. So again, just a level set. This is so that we can kind of all bootstrap our knowledge and get thinking the right way about machine learning and what it actually is, because it seems to be a catch-all term these days that gets thrown around a lot with a lot of misuse, in my opinion. And so I just want to set the record straight, make sure that we're all talking the same language. At least we are. Your clients might use different tech terminology, or they might think that you're using machine learning or artificial intelligence or something. I just want, and that's fine for them to use that terminology, but I at least want you and I to be on the same page about what it means to us. So let's keep that in mind. So to kick things off, I like to start with this XKCD that came about a few years ago, and you know, I'll let you guys read it, but the gist is obviously that it was really hard to do certain tasks with computers at the time when this came out, which is I think like 5 years ago. If you gave a computer a picture of a bird and asked it to identify that bird, or just, is there a bird in this picture, that was super difficult to do. Surprisingly so. Traditional machine learning and image processing techniques were just not good enough. What's funny about this in particular too, these days, this is now like trivial. The technology that makes this sort of stuff possible, using advanced algorithms, using advanced hardware, that is all now stuff that can run on your mobile phone. It is readily available to everybody. The algorithms are well known and well understood, and they're things that can be utilized. But in general, this is an example of some machine learning in action. All right, but pivoting on to kind of our main presentation here. So again, this is the Machine Learning 101, aimed to bootstrap your knowledge. Let's start with a definition, like we might expect. So machine learning is a subset of artificial intelligence that often uses statistical techniques to give computers the ability to perform tasks with data without being explicitly programmed. So I want to break that down a little bit into kind of what it means to me and why I like this as a definition. One, I want to point out that this is a subset of artificial intelligence. We're going to touch on that a little bit. But machine learning is not artificial intelligence. Artificial intelligence is not machine learning. Machine learning is one component of the broader concept of artificial intelligence that goes along with most definitions. I'll put it that way. Obviously, that definition's being a little overused these days. But anyways, really focus on it is statistical techniques. So these are very math intensive algorithms. Thankfully, they've become really accessible through the use of frameworks and other tooling. But really, machine learning gives computers the ability to perform tasks with data without being explicitly programmed. And so the general topic here is, and why this is so powerful of a concept, is that by learning these algorithms, by learning these concepts of things like regression, things like classification, those are concepts that are algorithms, but what they can be applied to, the sort of tasks and business challenges that they can be used to solve is vast. It's really, really vast. It can be used to solve tons and tons of different problems if you just know the fundamentals. And for anybody that's interested in machine learning and data science, that's a fundamental concept. Because oftentimes, and I'll just speak like from my own personal experience, it's not enough to know the algorithms. You also have to recognize the challenges that a business is having, and which of these machine learning algorithms is most appropriate and should be used, and how do you evaluate whether or not they're any good. So let's get into some more concrete details. First, again, I want to clarify some terminology that we heard. Machine learning is not artificial intelligence, nor is it deep learning. These are three distinct terms. You hear them thrown around a lot in literature and blogs and things like that. They are not the same, so don't confuse them. Artificial intelligence in general is a giant topic that touches on many, many different aspects of computer science and artificial reasoning and intelligence and vision, and it's just massive. And this is by most definitions. One part of artificial intelligence is needing to understand machine learning. Machine learning being this process of analyzing data to make predictions, if you want to think about it that way. One of the techniques within machine learning that can be used to make these predictions is known as deep learning, and that's been a modern advancement that we could get into in another time. And no questions. Okay. Like I said, every once in a while I'll pop back here, check to see if there's questions. There'll definitely be time at the end to continue, but just for the sake of time. So let's also talk about some terminology. We need to lay down like some frameworks so that as I'm going through this deck and I start saying things, you guys understand what I'm talking about. So we usually in machine learning and most standard types of machine learning, but really almost all of them, data, we need to be thinking about data represented as multidimensional points with one or more attributes. So think of a table of data, a giant matrix of data that you could have. So here we have some arbitrary data, length, weight, and color. Don't even know what this is. Doesn't really matter. It's some data. Wanted to point out that these attributes, well, we'll talk about it. Each one of your columns, oftentimes that'll be referred to as a feature of your data or an attribute of your data. Features can be numerical, like we have here. They could be categorical, like we have here. Like it looks like there's a red and a blue category, just one of two kind of categories. Or it could be freeform text. It could just be, whatever it might be. Really, it doesn't matter. It's data. Usually they fall under a few different categories though, like that, like categorical or numerical features. Each row, each data point is often referred to as a feature vector. So this is a combination of all of your features that make up would be known as like one observation. So if this was, I don't even remember what my example really here was, but let's say, I don't know what's red and blue. Maybe these are flags or something like that. That's the length and the weight of a flag and its color. It doesn't really matter. All of those attributes that make that up, all those features that make it up are referred to as a feature vector. Okay, so that being said, will this be posted after? I think YouTube posts this automatically. I can try to double check on that. I'm not really into the YouTube streams, but I think this gets posted automatically when I stop the stream. Okay, two main categories of machine learning algorithms. We're going to go through them both. One is the category of unsupervised learning. This is really discovering hidden structure in what we call unlabeled data. We'll unpack that a little bit. The other is supervised learning. This is analyzing labeled data, quote unquote labeled data, and produce an inferred function what can be used for mapping new examples. And I know that that's a mouthful, so let's go through some examples that are a little bit more easy to understand. So I find it useful to associate unsupervised learning along with these common questions or statements. And I brought this up again because as data scientists or as people that want to get into machine learning, you need to be able to identify when a certain client or a business or just anybody in a company, what sort of problem do they have? These are some common questions and statements that might lead you to think unsupervised learning. So oftentimes you'll just be handed like some data set, some table of data, some Excel file is probably super messy, but they say like, tell me something interesting about this data. Like, tell me something I didn't know about this. Can you find anything inside this mess? Any sort of structure, any sort of meaning? People want to know, like, is there a lot of like groups or clusters? They might not call them like that, but they might say like, is there any sort of order in this data? Or is it just like truly random? Are certain features more widely distributed than others, or are they correlated? Are they related? Are some features similar to others? Are some of my attributes really similar? That could be like some sort of correlation analysis. And then oftentimes, like, are there any anomalies or irregularities within my data? That's really common to find like outliers. All of these would be questions that I might think off the bat without asking anything else, which we'd obviously want to do, without asking anything else about my client, my business use, I might start thinking already this is an unsupervised learning challenge because there is no direct prediction that's being made. None of these are saying predict revenue next month for me or predict color based on height and weight. No, these are more like general about the structure of my data. So those are the sort of challenges that unsupervised learning might have. So for example, let's say that we have this data set to the right. So if you'll notice, this is, again, some heights and weights and colors. We might want to ask some of these questions on the left about this data. We might want to identify, a natural question is, are there any clusters in this data? Are there outliers in this data? So that it can help better identify kind of the groupings in this. This is an easy one to look at because it's just kind of two-dimensional, but oftentimes we're given data sets with hundreds of features, and trying to understand, are there groups within my data that are similar, is really powerful. Think about user segmentation. So let's say that you have a big database of users that are making purchases, and you go onto Amazon, and what do you want to do, right? A user purchases something on Amazon, you want to be able to recommend other purchases. Well, let's say that we kind of have binned all of our customers into distinct groups of similar activity that have made similar purchases. Then by structuring that way, how do we break up our purchases in our groups? Then when somebody comes in and adds something to their cart, we can look up, what did others that are similar to this person add to their cart as well, and give recommendations. So again, unsupervised learning can help. One way of identifying this is through clustering. So clustering is grouping a set of objects in such a way that objects in the same group, also known as a cluster, are more similar. So let's just take a look at some of these like random points, or apparently random points on the screen. This is just like a dummy data set. It's a natural for our minds, and you guys might already be doing this just when you look at it, for your eyes to already like kind of pick up on maybe some groupings. It looks like there might be kind of a grouping here and maybe a grouping down here. Maybe these are two distinct groupings. Those are natural things. And so it kind of begs the question then, like, what about these, what makes them similar? Or is this like a group of, maybe these are height and weight, and this is like one species of animal, and this is another, and another, and another. Just looking at this raw data, you can sometimes find those sort of interesting things. And so one way of achieving this, and we're not going to go through the details, but you'll just read about this if you get into clustering at all, is the concept of k-means clustering. And I'm going to play a little animation, and it plays really fast. But the general idea is that you start by just randomly dropping points on your kind of your feature space. So let's say that we just drop, we think that we have 4 clusters, so we drop kind of 4 dots just randomly on the page here. Then what you do is you move each dot, you find for each dot, what are the corresponding observations that are quote unquote closest. So you can just find like the distance from these random points that you dropped to all of our actual observations. And then we move our initially random point, sometimes called a mean, to the center of its closest item. So let me just play this through, and it'll kind of make a little bit more sense. I wish it played a little slower. It's a GIF. So these green dots are basically initially just randomly placed. And then the red lines correspond with the quote unquote nearest, the nearest observations to those points. And you can kind of see this is an iterative process that continuously calculates what is the nearest neighbors I have to each one of my green points. Then we're going to adjust our green points to be in the center of those nearest neighbors, and then redo it until everything stabilizes and there's no more changes. And so this simple algorithm can be really powerful, because at the end of it, and it only shows up there for like a flash, but you can see the last step, it kind of has like automatically identified kind of those 4 things that we initially spotted, maybe just by hand. So k-means clustering, one of many different clustering techniques. It's just one method that I just want to get across as an automated way to take your data, and without knowing much about it, you could come back to your client and say, hey, it looks like there might be 4 clusters, and these are kind of the clusters of points within your data. Maybe we could inspect those clusters then and determine like what makes them different. Maybe these are different spending habits at a client or something like that, or amongst your customer base. Lots of great applications for clustering. You'll see that pretty frequently in it. Any questions about that? Let's take a look. Oh, yeah, fairly certain it does. Okay. So on to supervised learning. We said that this was kind of the other major kind of category of machine learning. This, to be completely fair, is the much more, in my opinion, applicable one to most business challenges. So let's go through some of the common questions that might lend itself to a supervised learning challenge. You guys might have already heard this from your clients already. So like, what features affect our company's turnover the most? What will my profits be in the future? What species is this flower? What action should we take to improve our revenue? What type of car is in this picture? Can you convert this audio recording into text? So the key differentiation here is that there's always some sort of target variable, target feature that these questions are interested in. So in this case, it's trying to understand things as related to company turnover or profit or a species. It's making a prediction or understanding what goes into a prediction in some cases about these sort of things. These are all what we would consider supervised learning questions. So if we take a look at our data set from before, kind of a supervising learning question might be, given this data set of height and weights and colors, let's say a new measurement comes in, and I've just gone out and I've measured the height and weight of a new item, and I want to predict. I forgot to write down if it was red or blue. I want to predict what is the likelihood that it's red or that it's blue. What is most likely? I want to make that as a prediction. That predictive aspect of that is what makes it kind of a supervised learning problem. In addition, supervised learning can be broken down into two subcomponents: classification problems and regression problems. Classification problems are predicting a discrete class or a label, and regression is predicting a real number value. So for the classification example over here, we just went through an example of that where, given a height and a weight, it's a natural question to ask, what would the color be, or what would be the predicted color? Because color is discrete, it's only one of two states in our case, it's only red or blue. That lends itself to what's known as classification. That's a certain subset of these algorithms that would narrow your choice down. On the other hand, if I measured the weight and I had the color, and I wanted to say what's the most likely height, that would be a regression challenge. So again, classification is determining something discrete, like a class or a label, red or blue. It could be numeric, but oftentimes it could be like a 0 or a 1 or true or false. You see a lot of those, or some kind of 3-state thing. Regression is more about predicting a real value, a number. And so with regression, it'd be trying to find like where this X would fall on this in a statistically significant way. So one way that I wanted to determine this, and usually this is much more interactive because I'm doing this live like with you all, is I just want to touch on a couple different things. One is like the simplest classification algorithm that I probably can even think of, and that's what's known as k-nearest neighbor classification. So the idea here is that, let's again set up our problem. I've given you a ton of height and weight and color measurements that I've taken about some sort of items, doesn't matter, into the wild. And now I give you a new observation, a new height and a weight, and I ask, what do you think the color is going to be for this new item? Probably intuitively, kind of looking at this the way that you might, the simplest thing to do is what we would call k-nearest neighbor. And the idea here is that we find the the k nearest points. In this case, I chose 5 as my k. Choose the 5 nearest points by their Euclidean distance. So you calculate the distance from this x to all the other points. You sort them by the distance, and you just take the 5 top ones, the 5 closest ones. And then you do a voting scheme where you just vote to say, of these 5, which one of my classes, which one of my colors has the most. So in this case, there's been 4 blues and 1 red. So we would take our X and we would say, you know what, we predict that this is going to be blue. So this is just one method of what's known as classification. Like I said, it's probably the simplest one. There's many, many pitfalls to the k nearest neighbor, but it's an easy one to kind of get started with and to think about like conceptually. All of the algorithms that are classification algorithms are just trying to basically guess blue or red. That's all that they're going to try to do. And they do very, very sophisticated things to do that, way more sophisticated than this. Some with better success than others, and it really depends on your data set. It depends on tons of different factors. But nonetheless, all of classification is really trying to do is guess blue or red. We just showed you one algorithm, the k nearest neighbor classification algorithm. Linear regression, many of you might have done this and used it like in Excel or something like that. So again, regression in general is trying to determine a numeric attribute of an unknown by modeling a linear equation. So as we said before, again, I give you a bunch of points that are height, weight, and a color. And now I give you a new point, and I've given you the weight and the color, and I ask you, what do you think the height is? Linear regression, what that tries to do is it tries to fit lines that go through the points. So in this case, I have tried to fit 2 lines, one for my blue points and one for my red points. And then I simply just play out the analysis where I take this line's equation, which is the weight, and I plug in the weight, and it'll give me whatever my color is going to be. Linear regression, there's tons of different ways to actually do this kind of line fitting. There's pros and cons to each one of them. It doesn't necessarily have to be linear. You can do nonlinear regression. Lots of different variation. But again, I just want to give you a flavor for the sorts of challenges you might have, because your clients might be asking you to predict numerical values, stock prices or revenue or customer satisfaction numbers. I'm trying to think of some of the projects like off the top of my head. I don't remember all of them, but nonetheless, so if you have these sort of questions where your client's starting to ask you to forecast things or generate numerical predictions, regression techniques in general are probably what you're looking for, and linear regression is one that might get you started. So in general, I want to talk about like the general steps for supervised learning, since most of the time that's what you'll be working on. The first is data acquisition and preparation. So we have to be acquiring our data somehow. Either our client needs to be giving it, or we need to be figuring out how we get it, or how do we scrape it. But we have to get the data, and we have to do this fast. Without the data, we can't do much else. So we need to start acquiring it and understanding it, preparing it, oftentimes cleaning it, removing bad data, faulty data, incomplete data, things of that nature. Data acquisition preparation can take a ton of time. The next is splitting data into training and testing sets. So it is important for a lot of our algorithms that we do this step where we don't necessarily train and that's using a term that we haven't really introduced yet, but as we're building our models, our predictive models, the fear is that you give the model the answers to the questions that you're about to ask afterwards. So if you think about it, let's say that you're college students, you're about to take some exam, and it's a multiple choice question. And before the exam, I just give you all the questions and the answers, and I say, okay, you're not going to have this on the test, but I want you to, this is what the questions are going to be like tomorrow. So you go home and you just simply memorize all of the questions and answers. You come in the next day. If you don't ace that test, like, first of all, have you actually learned anything if you ace that test? I would argue probably not. You've learned how to memorize some questions and answers, which isn't truly learning. If I ask you a new question that you haven't seen on the test, or I put a new question on the test that you haven't seen, I don't know if I'd have any confidence that you could get it right. And so I don't think that you would have truly learned. And what we would say is that you haven't generalized your knowledge to be applicable outside of that training data that I gave you, which was the actual questions and answers. So the idea here is that we split up our data into a training and a testing set, and we build these predictive models off of a training set, and then we take this new set of data called our testing set to evaluate, is our model any good? Did we actually teach it? Can it be applied to the real world? Because most of these algorithms, or any of the ones that are like worth their salt, they are really good at memorizing things. That's like the biggest worry. You do not want your models to just have memorized your training data and then be useless on anything else that it's not seen before. That defeats the purpose. If it was just a challenge of looking up values, we'll just load those values in a database and we'll just look them up like we do anything else. So to make our models predictive, we need to be able to split our data in training and testing. From there, we train our prediction model with the training set, as I just talked about, and then we evaluate the model's performance on the testing set. So we've separated those two things out. If those numbers look good, and we can get into the details of like what makes a good model and how do you evaluate this, these are all kind of like loaded terms that we could unpack and dive deeper and deeper onto. If those look good, then we can be confident and deploy and actually use our model. I'll be crystal clear that without these sort of evaluation metrics and without following these steps, which I'll guide you with, I will be questioning you guys throughout the class of these things, because we don't want to go live with something that's garbage. We can't go to our client and deploy a model that is no good without them at least being made aware of, the caveats with it. It's disingenuous to them. It's disingenuous to their end users. And so best practices just say that we need to dot our I's and cross our T's and make sure that we're following proper methodology to ensure that the model that we ultimately use is statistically valid. And hopefully it has good results, and meaning that it's quote unquote accurate. Questions? No questions. And so as we kind of tail off on the end there, and I was mentioning one of the important aspects is evaluation. It's probably the most important aspect in a lot of ways. We need to be able to understand that we need to evaluate and measure our performance. Without being able to properly measure how we're doing, then we can't make any changes, because we'll never know if the changes that we're making are doing anything. Are they helping or are they hurting? You're just blindly reading blogs or just trying things, but without setting up, how are you going to evaluate these changes to see if they're better or worse? And then it's all kind of for naught, in my opinion. And so there's a number of different ways to do that. Again, I'm going to focus on I'm going to focus on supervised learning performance metrics. And classification metrics, so remember, classification again is evaluating a discrete value like red or blue, true or false, cat or dog, male or female. Usually they're binary, but they don't have to be. They could be red, blue, green. There's metrics like accuracy. We've all heard that term. We're going to talk about why there's some issues with that term. Classification also has the concept of a confusion matrix, which we can unpack in a later one, an F-score, area under the curve, ROC curve. These start to get more and more complex, but also more and more statistically accurate. We'll talk about accuracy in a second. And then in regression, we often have things like the mean squared error, the mean absolute error, the R2 score. If you've done anything with like linear regression, and R2 score is really, really popular. If you start getting into other types of regression, R2 scores aren't quite as common. You see some of these other two ones, mean squared error and mean absolute error, along with other ones. These are just a sampling of some of these. But again, as you're getting started with your projects and as you're identifying that, okay, we think we have a classification problem, this is our data that we have, this is what we're going to try to predict, how are we going to evaluate it? We need to be trying to look at these different items and determine what are we going to say we're really going to use to determine what good means. What is that definition? No, I guess I didn't quite get around to accuracy in this one. Nope. Okay, so the problem with accuracy, I have another deck that we could dive deeper in for those that are interested, maybe on another night. The problem with accuracy is it really depends on your starting data set. So let's say hypothetically in that example that we had before with weights, heights, and colors, let's say that 99% of my data set, let's go back to it just to take a look. Let's say 99% of my data set here was red dots. Everything was a red dot except a single blue. If you come to me, and let's say that there's 100, if you come to me, 99% of my data was red, 1% is blue, it is trivial to make a classifier that is 99% accurate, right? Because all I'll have to do is I will just make a classifier that predicts red every single time. And then no matter how I slice my data and I try to evaluate it, everything's going to come back and say, yep, you look 99% accurate. Fantastic. I will question you guys hard if you have some numbers that appear like this, if those numbers are too good to be true. So the key takeaway, though, for accuracy, I won't harp on it too much longer, is that it has a lot of pitfalls, mainly when you have what's known as imbalanced classes. When you have a disproportionate number of reds to blues, or males to females, or species A to species B, whatever it might be, if those numbers aren't close to like 50-50 or however they're split, if they're not similar, accuracy really doesn't mean a lot. So you need to, if you're going to be reporting out accuracy numbers, you need to find ways to adjust for that. Sometimes there's not a good way, and that's where some of the other performance metrics can also come into play. Okay, and so I want to just say, this is like my all-time favorite quote, and I say it all the time, and I catch myself saying it all the time to myself. And I don't know if you've heard this before, but if all you have is a hammer, every problem looks like a nail. And the point is, and I think this holds true to like computer scientists in general, we cannot only have a hammer in our tool belt because the world is not made up of nails. Every computer science software engineering challenge is a little bit different. If it was all the same, then there would be no need to do the practice, right? It would just be cookie cutter. We'd have everything already automated in the world. No, we like to work on problems of things that we've never seen before. Some strange type of hex nut bolt. Who knows? It is our duty as software engineers to find the right tool for the job, to identify the right frameworks for the job, and to solve it as cleanly as possible, given all the constraints that we have. The same holds true for machine learning and data science. There are many, many different ways that you can often analyze these things. We can't go into every problem and say, we got to use k-nearest neighbors or linear regression. Those aren't, there's such great variety of different tools out there because not all of our problems are nails and each one's a little bit different. And so it's going to be our due diligence to try to evaluate different types of tools to see which one is best. So try not to go in with preconceived notions of, what sort of technology you might use, what sort of algorithms you might use. Although many of you are probably getting new, so it's kind of like you're a blank slate, which is great. You get to kind of learn all this stuff from scratch and do that. So please try to keep open minds when you're thinking about your problems and you're thinking about the possible solutions and technology. Just reading up on a blog post that says TensorFlow is the greatest thing ever, that's fantastic, but that might not be the right tool for your problem. To get that point across, so there's a very popular library called sklearn or scikit-learn. It's a Python library. One of the like industry standards. It's a great place to get started for sure. I use it all the time. Absolutely fantastic. So I just want to show you. So this is just one library, sklearn. This is the supervised learning section. This is like their table of contents. You'll notice under linear models, which you can think of this as like linear regression, they have all these different types of basically linear regression. Each one, 1.1.1, 1.1.2, 1.1.3, all of these have different pros and cons and trade-offs and considerations to make. I'm not going to be asking you guys to like exhaustively do all this. We could talk about maybe some of the best ones, or the most common ones, I'll say. Maybe best is a terrible word there. Some of the most common ones. And if we have proper evaluation metrics in place, we can just evaluate many different types of these and see which ones work best for our problem statement. So with today's frameworks, how easy they are to work with, modern computing technology, sometimes the best approach is just a shotgun approach where you just try many different things and see which one works best with your data. So this probably doesn't come through very great on YouTube, but I want to scroll down. These are all different types of supervised learning algorithms that this one library, sklearn, provides. Granted, a lot of these are used with in other libraries as well, but nonetheless. And so to touch on that, there are a lot of different libraries out there. I kind of bucket them into two different categories. Others would probably fight me over, blending some of these. There's definitely some gray area, don't get me wrong. In general, I see there being kind of two buckets: general purpose and advanced use cases. So I would say things like R and some of its more common packages. R is a statistical language that's like really good for doing machine learning. For the most part, very, very common, tons of activity, really popular in both the professional world and in the academic world. We just went through sklearn. That's a Python library that's really, really popular, again, in industry, getting more popular in academics as more and more are starting to learn Python from a younger age. SAS and SPSS, you might have heard of them before. These are more enterprise-grade solutions, so they're not open source. SPSS is made by IBM, or at least it used to be. I think they might have changed recently. Anyways, and SAS is its own company, huge multi-billion-dollar company. Pros and cons to each. Sometimes organizations really like some of these bottom ones because they have enterprise support, so if something breaks, they can call somebody and get help. Where if you're up here, you're using open source stuff, and if it's broke, you better fix it, or you got to figure out workarounds, and there's just a little bit more risk there. But this costs a lot of money, and the top does not cost any money. So pros and cons. On the other side, we have more advanced use cases. I think all the ones I've listed here are actually open source. But these are more specific, I would say, and not as general purpose. So the ones over on the left are more general purpose to supervised learning, unsupervised learning. Once you start getting into like more like really cutting edge stuff, you might need some of the libraries on the right to do various things. So for example, TensorFlow is really great at building neural networks and deep neural networks. So if your problems are geared that way, which they might lend themselves that way, image recognition, audio processing, sometimes those kind of require more complex analytical models like neural networks. TensorFlow could be great. Caffe 2 is great for like image processing, image recognition tasks. Spacey is fantastic for natural language processing. Bottom line, this is not an exhaustive list by any means. The only reason I wanted to bring this up is to say if you do have a very specific use case, your business person is asking for a very specific thing, there might be a library that's more specialized. Maybe that's a better way to put this, is like specialized use cases. You have some specialized like forecasting or neural networks or whatever it might be. There might be a library that makes it easier. You don't want to have to reinvent the wheel from some of these general purpose ones. You're just going to end up writing way more code. Your code's going to be buggy as all get out. It's not going to be as performant as some of these more specialized or advanced tools. I hope that's clear. And again, I can guide you through some of the landscape as we start to understand our clients' challenges more. I've used many tools. I'm not saying I've used every tool. I can probably help point you in better directions than others to make sure that you're using like some industry best stuff. Hammer.js. Yeah, what was Hammer.js? I don't remember. I knew Hammer.js at one point. I thought that was like animation or something. Anyways, they do have these quote unquote like algorithm cheat sheets out there, which I kind of find funny. They can be really useful, to be quite frank, especially as you're just kind of getting started. But and there's a number of different ones. This is like the Microsoft Azure one. You basically start up here, and then they just ask you these questions. Are you trying to predict future data points? No. Use k-means clustering. You can see, well, we already know what kind of that is. So if you're not predicting anything into the future, or I don't know, that every cheat sheet has its own little quirks. But anyways, if you are, then come down here. Are you predicting categories? Then you're going to come up here and you're going to talk about classification, and this is multi-class or two-class, and here's regression, there's anomaly detection. Anyways, some of these at the end of them, kind of at the leaf nodes, are different machine learning algorithms for doing some of these sort of things. And I was just going to see, so like here, for example, is linear regression. We talked about that a little bit today. Support vector machine. Let's see. I don't know if they even have k nearest neighbor. Doesn't look like they even have k nearest neighbor on here. But anyways, the bottom line is there's cheat sheets out there that can kind of help guide you and point you in the right direction to make sure that you don't go too far out of the weeds. And some of them are pretty good. They show some different reasons why you might choose one or the other, explainability and so forth. So again, this whole purpose was just to point out that there's a lot of different things out there. Don't get overwhelmed. There's plenty of help for you. If we set up our processes and our methodology correctly, where we have proper training and testing splits, if we have our evaluation criteria established ahead of time, then we can try a lot of different tools and see which one works best for us. So that was the main, that was the main stuff that I was going to go over today. I have other material for some of these more advanced topics. I generally hold off on those and basically just present them by request. So if teams or individuals are interested in like diving deeper into supervised learning, unsupervised learning, image recognition, deep learning, these sort of topics, I have material. I've done this stuff for a long time now, 10 plus years. I am more than happy, I'd be ecstatic to talk with you guys more about it. But really, this concludes kind of what I had planned for tonight. So I'll open it up to any questions you might have, and I'm happy to elaborate on anything. Give it a few more minutes in case you guys are typing something, but otherwise, that's it for me tonight. Okay. So no questions probably means that you guys have a bunch of questions that you want to ask me when we get to class. I don't know what's going on Thursday. Now that I have you all here. I know that my wife just got a message. She's an elementary school teacher. They canceled Wednesday and Thursday for her. She had off yesterday. She had off today. So I don't know. If the weather is going to be really terrible, then I don't know what we're going to do on Thursday. It might be another open day. Maybe I'll dive into one of these for you guys that are interested. But otherwise, appreciate everybody joining. The recording should be up on my site. I'll try to send out a link later. Happy to talk with you more in the upcoming weeks. So have a good night. Stay warm. Be safe. Don't do anything dumb in the cold. Bye.